Hey there again. I thought it'd be a good idea to do one final video to just sort of wrap up the project and talk about a few things that didn't fit into other videos. Basically, what I want to do in this video is talk about the final results of the project. I also want to talk about the model structures in the project, particularly why I have so many. I'm going to be talking about the hyperparameter tuning process, which is a process to get the best final results you can after the model is trained. And then maybe one last section on just kind of final thoughts and ideas on how to get how you can get even better results in a project like this. Okay, so these are the models that I trained at one point or another during the project. I'm just going to go through and explain why I created each of them. So basically, the first one was sort of the default model used in the project. That is just the recreation of their wave-to-letter model. I actually had a small error on this one, which I created, which is why the new models will exist. But just to go through that model right now, we have our one-dimensional convolution stacked on one another, the output of one being fed to another, and then a log softmax of the outputs. So that was our vanilla model for the letters. So as you can see, for our letters we have 29 output classes for 28 characters, or sorry, 26 characters of the alphabet, plus the space character and I think apostrophe or comma. Which bars? Yeah, apostrophe. And then also one additional one for the blank character, which is used for the CTC loss and is important for the decoding. So that's what I had there. We have, basically for each of these models, we have an equivalent phoneme model. So the phoneme model is identical in structure, except for the fact that it has this 41 classes. There are 40 phonemes, and then there's the one blank character for the phonemes. And then I actually, it looks like I added the difference in here. One of the things that, so before I found the error, actually, I'll just talk about what the 2D models mean. So for our one-dimensional models, we have those 13 MFCC channels coming in, and they are just stacked on top of each other, and then for each, so we have and then we have the differentials of those channels, so 13 times 3, and then we have our one-dimensional convolution going across those. Basically, what I thought would be interesting to do is try and force an association between so a channel, an MFCC channel, and its derivative and the second derivative. So what I did there is I created this kind of like 2D input, so those channels are stacked together, are associated with each other, and then we have a 2D convolution on our first layer that looks at those three channels together, the three kind of derivatives together, and then outputs that to a 1D channel. Otherwise, it is the same. And then we have an equivalent one for the phonemes. And then later I realized my slight error, which in the models, in the model structure, which is I had forgotten this ReLU on the output. So technically there should be a ReLU function such as this right here. So surround within before the log softmax. I just spaced and I thought that you couldn't do like two activation functions on top of each other. Of course you can. Using the output we want a softmax, but there's no reason that we can't have ReLU values outside of that. So I remade the models. It actually did not make a significant difference, but I thought it was definitely something worth trying. So that's why I believe this test 2 model is identical to the torch model, except for the actual properly placed ReLU function. The difference between test 2 and test 1 is so this 12-layer, 11-layer business. So basically, what I got from this is when I was recreating I recreated the model based off this chart here, and they give 40 outputs. Despite the fact that it's called wave-to-letter, they have a 40-channel output, but you only need the 29 channels in my output. So I thought maybe this ratio between 2000 and 40 was important. So I kept the 40th layer, or sorry, I kept the layer of 40, and then I added this additional layer, going from 40 to 29. to my final 29 outputs. When I think that what you're actually supposed to do is have this 11 layer function and just go straight to 29 in the case where you're decoding to letters, and just go straight to 40 in the case where you're decoding to phonemes. So I also tried both of those out. I took out the buffer layer, so to speak, and did this test, and as it turned out, I actually got a significantly worse performance than the wave to letter torch that had that accidental buffer layer. So that's why the test 2 came in. Maybe not the best naming convention, but I re-added the buffer layer and then kept the value. I had a similar problem with the phonemes. So with the phonemes, there were actually 40 phoneme outputs. So when I made the phoneme one, I was like, oh, this makes sense. They just probably have 40 phoneme outputs, and then they're not, I don't know, they're not including the blank or whatever. So by default this one was 11 layers, but then once I realized that there was a performance difference between the 12 and 11 layer versions, I decided to try it with 12 layers. So I have 2 here, one with a 40 output on the buffer class and one with 80, just to keep, I thought that maybe keeping the ratios similar might be vital. And this actually improved my phoneme performance. Before, my phoneme performance was, I think that the loss value was about at 1 for the default wave to letter torch, and it was about at like 1.3 or 1.4 for the phoneme torch, and I was wondering why there was this discrepancy. I just chalked it up to like the data set is slightly smaller. I think I mentioned this, I know, in my data video, but not basically whenever it couldn't accurately give the phonemes of a word, like if it hadn't seen the word before and that word wasn't in the dictionary, we just discard it. And I thought, well, you know, the training set is smaller, so I guess it makes sense that the performance is small. The performance is not as good. But when I added this 12th layer, I was able to get just about the exact same performance. So I was pretty happy that happened. Anyway, hopefully that explains all the models here. There's also this mini model. That's just a smaller version of the model. I think when I was doing this project at the very start, this was just a way to check if the training would work and have it be less computationally expensive. But yeah, hopefully that all made sense. Hopefully all these models make sense. I'm not sure if I talked about the 2D results. The 2D results they weren't a disaster, but they weren't as good as the default model structure, but it was something worth trying. So I also want to talk about the process of selecting hyperparameter values used in this project. So I consider this project to have 2 hyperparameters. I remember which is pretty low. I remember one of my projects, the DQN Turtlebot project, had about 10 hyperparameters or so. This variable was called hyperparameter list, but they're not really all hyperparameters. But basically, hyperparameters are the parameters that affect the function of maybe, in this example, it's our decoding algorithm. Our hyperparameters affect the behavior of the decoding algorithm, but they are parameters that we cannot find by just training our acoustic model. So just to do a quick review of what these parameters are, our n beams are the amount of beams that we're keeping in that we have during our beam decoder. So that's the amount of hypotheses that we have at any given time. And then the other hyperparameter is this c-text, and that's basically how heavily we weight the input from the language model relative to the acoustic model when we're making those predictions for each input. For the n beams, basically you would get better results as the amount of beams go up. You really, I don't think that you would ever get worse performance, but your algorithm will be running slower. So that's really not one where we have any, your decision will be based off your requirements rather than, the performance of, rather than some kind of output score. For the language model, or for this c-text, we can find an optimal value for it. So for that, I have 2 functions here. I have one called binary search, and I have one called grid search. Grid search is sort of the traditional method where you set sort of a step and you set a range for this variable, and you just simply test the outputs. And if you have some kind of output metric, so in this case word error rate is our output metric, you can do that and find where the optimal value is. The binary search is a little more convoluted and maybe a somewhat misguided effort by me. But basically what this does is it's a similar process. You have your range, but the idea is you're sort of cutting this step in half each time depending on the result that you get and whether it was better or worse than the preceding result. So let's just say that we have a default error rate of 80%, and then we jump up halfway, and if our error rate is better, then we would continue, but if our error rate is worse, then we would double back. But in each case we would halve the step. So and like that kind of zero in very efficiently, which sounds good in theory. The problem that I found with it is if the differences between the scores at those steps is not very high, it can be a little sensitive to, say, errors. And the word error rate is an algorithm. So the decoder and the word error rate function both take a while to run. So having a high number of samples is hard as well. So I think it's kind of better to just go over with the grid search. Find you'll be able to find with a high step count where the best area is, and then you can just set the grid, and you can perform another as many grid searches as you need to kind of go over with a fine-tooth comb and find the best value. So this algorithm here, not too complicated, just loading models. We have our predictions at each one, and we compare the word error rate. So we compare our predicted values with the target values. We have our word error rates, and we can take, I have two different averages here. I have just kind of like a naive average, which just takes the average for each input, and we're going to take the average of those. And I have one that has kind of like a weighted score, so it's a word error rate. So the idea is that input sentences with more words should weigh more heavily than input sentences with few words. Anyway, so I was able to graph these. Let me just open this, save plots. And this is what this graph looks like. So you can see we get a pretty steep fall off down to around 0.8. I think this is 0.95 here. You can see, so you can even see some of the sensitivity here. Like this is probably where the optimal value is, but just it happened to be sensitive to certain samples used. I think I used 40 samples, or yeah, 40 samples. And then it goes back up. So yeah, that was my hyperparameter process for this video. Hope it made sense. Okay, so I said I would talk about ideas for improving the project, even though I'm sure that there probably are small things that I could do within the code base to improve the project. Basically, the main thing that I didn't do is I should have used a larger data set. I used this 100-hour data set, but you can combine, I suppose, to get the most clean data, it would make sense to combine these two data sets and then maybe just use one of these one of their specified test data sets as your test data set, even though that doesn't let you control the split as I did in this one. But basically we were working with a slightly reduced data set in this project than what is actually fully available from this ASR corpus, which was a great resource and is kind of like the standard resource for I believe these for the academic kind of speech recognition projects that exist. With that, I just want to say this project was a very interesting process, a very long process. The end results were good. Not great. The word error rate is, it's not that I expected to touch world-class error rates, but I'm definitely below the wave-to-letter error rate. So how much that would be rectified by using these is maybe something that I'll investigate in the future. It would take a little bit of a couple changes to get that, but it would be interesting to see. But I just want to say, yeah, thanks for watching these videos. I hope that that you enjoyed them and that you're able to learn something. So thanks so much. Bye.